Part C, Introduction to Hashing. This search technique. So here, I want to quickly get to the topic. So here, in the introduction part, first question, why using hashing? So what's that? Let me give you some quick, simple introduction. Right now, so let's look at our search algorithm. Search algorithm, we have linear search or sequential search. Linear search, we know it's an unordered array. All right? And if we use the big O notation, that's big O of n. The efficiency. So then the binary search. Ordered array. Then much faster, big O of log n. Okay? And these two algorithms, we need to use comparisons. And when we use comparisons, so when we use comparisons, we need to get the order information. Order information, that means we need to know equal, less than, or greater. Okay? All right. So that's the basic information. All right. So now there is a new idea about searching. Still search. Okay? Search, the third method. The third. Okay. All right. So this hashing. Okay? This hashing belong to search. Hashing, also unordered. All right. And the comparison. So here, the operation. You also do comparison. You do comparisons. You do not get order information. Okay. So not for order information. Okay? Not for order information. You can see the special thing, special part. But not for order, because in your mind, whenever you do comparisons, you think you always get order information from the comparison, right? But there is another comparison, not for order, it's for matching. Okay? Not for order, for matching. Matching or not. Okay? So two data pieces are equal or not. Matching. Matching means equal. Okay? Not matching. Not matched. So not equal. Okay? So not for order, but for matching. Okay, so that means equal, equal or not equal. Let me just write equal. Only these two states. Okay, not equal. You don't need to know greater or less than. Okay, it's not important. You only want to know equal or not equal. Okay. So no order information involved. In this one, no order information involved. Okay? So this is the property of hashing. But what's the benefit? So when we do this way, what's the benefit? The biggest benefit is its efficiency is extremely fast. Big O of 1. Big O of 1, that's the average case efficiency. Average case efficiency. Okay? So you can see even faster than the binary search. Think about that. You know, for unordered data, it can do faster than the binary search. How about that? Yeah. But actually, there is a building cost. Yeah. Because when you build a hash data structure, you rely on a special data structure. The build cost is bigger of n. There is a build cost. You need to build a hash table. The build cost is bigger of n. Okay? After that, after you build it, then when you do the search, so you get average case bigger of 1. Okay? Yeah. So that's the, you know, why this technique is very important. Yeah. All right. So let me talk about the main ideas of this technique. Yeah. All right. So as an introduction, first I need to give the story from the very beginning. Yeah. You know, this part as the background. Yeah. How to find a data item with a given key. Yeah. So we need to answer this general question with a given key, search key. Yeah. Okay. So you have data, you have array of data, and a given search key. How can you find an element in this array matching the search key? Okay, all right. So given a collection of data dynamically, yeah. So we talk about dynamic data last time a lot. So here still also dynamic data. Okay, all right. Each data item is identified with a unique key. Yeah. Unique. Yeah. The key must be unique. Okay. Otherwise, you cannot call it a key. Okay. Yeah. The definition of key, all the key values must be unique. Yeah. Yeah. ID. You can use it as ID. Yeah. Question: how to make your data search efficiently? All right, the question is very general. Yeah, yeah. And to answer this question, you have freedom to choose appropriate data structure. It's not given. You do not need to use array. Okay? Yeah. So if you want to use more advanced data structure, you can use it. Yeah. So you need to design your data structure here. Okay? Yeah. All right. So you have freedom to choose it. Yeah. But you need to, when you design your data structure, keep this in your mind. Handle dynamic data efficiently. Remember insertion, deletion, right? So here, mainly, talk about insertion operation, deletion operation, should be very fast. Okay. Yeah. Yeah. Supporting efficient insertion and deletion. Okay. All right. Here, let me do a chart. Examine our known search algorithms. Yeah. Linear search, binary search, index search. So this one, actually, I didn't talk about this index search, right? Yeah, I didn't talk about this index. But it's so simple, so straightforward. Yeah. The reason I put it here is our hashing technique based on this simple one. Yeah. Index search, what's that? Yeah. So I will explain soon. Yeah. All right, the data structure for all these, yeah, here, 3, all array. We use array, yeah, simple array data structure. Yeah. All right. Performance, linear search, big of n, binary search, big of log base 2 of n, yeah. Index search, big of 1. So what's the index? Yeah. Here I have to explain this index search. Yeah. Yeah. That's very simple. That's very simple. All right? Yeah. Given an array. Okay? All right. Yeah. Index. Yeah. We use the array indices as the search keys. Okay, that's simple. Array indices as the search keys, so they're unique, right? Array indices are unique. Yeah. All right, and it is fast, right? Yeah, because given array index, you can find the data immediately, right? Because you know the location, you just go there and read data from that location immediately. That's the so-called index search. Okay, yeah. So simple and fast, but it has a big problem. Yeah. Huge problem. So we can say, yeah, that's the reason in the real world situation, it is useless. Okay, yeah. The reason, so nobody talk about that, is because this algorithm. Oh, sorry, what's wrong? We're here. All right. It is useless. All right. Yeah. It has a big, huge problem. Okay. I will talk about later. Okay. Yeah. Basically useless. Yeah. But even if it is useless, why I put here, right? Because it gives us inspiration for this hashing technique. Okay, yeah. So the reason it's important is we get inspiration from this useless algorithm, and we improve it. Then we get an extremely important, fast, very useful in the real world, this hashing technique from this useless one. Okay. Yeah, actually, it's not useless, right? Yeah. So useless means you cannot apply it directly in the real world applications. Yeah. But for the inspiration, yeah, then it's useful. Okay, useful for inspiring our new idea, new solution. Yeah, that is useful. Yeah. All right. Ordering, so unordered data, ordered, unordered, yeah. All right. Dynamic, yeah. Dynamic, yeah. So linear search, because you do not need to put them in order, so the insertion cost is very low. Yeah. Insertion cost is low, but deletion cost is high. Yeah. So here, I should say yes and or no. Yes for insertion. No for deletion. Deletion because you need to find it, right? When you use the linear search to find the right element, location, that cost is too high. Big O of n, that cost is too high. Okay? All right. So that's problem. Dynamic. The costly because for insertion. Okay? The costly, for insertion, yeah. I mean, in general, costly, yeah, because you need to recover the order, in general, costly, yeah. Index search, yeah. Index search also, yes, no, yeah, because, oh no, yeah. Deletion, yeah. Oh, yeah. Yeah, let's say yes. Yeah, because think about the index given, then you do insertion, deletion very fast, right? Yeah, yeah. But it has other big problem. Yeah, it has another big problem. Yeah. All right. Efficient sorting. Yeah, because the data many times you need to provide sorted data in certain applications. But when you need to provide sorted data, how much is the cost, right? How much is the cost? Yeah. So the linear search, no efficient sorting. Yeah, because if you sort it, it's very expensive. Okay? You need to sort unordered data. So it is very expensive. The binary search sorting, very cheap because already ordered. Your data is ordered. You just return ordered data. Yeah. But index, there is no order. So if you want to get ordered data, then very expensive. Yeah. All right. Yeah. So that's the comparison for these three search algorithms. Yeah. So the new one, when we design a new one, yeah. All right, we need a new data structure. Yeah. For the performance, we like to keep the bigger of one performance. Yeah. Index search type performance. Yeah. It could be slightly slower, but we hope not too much slower. Yeah. Unsorted data, so we do not require, because if we put more requirements, then it's harder to achieve our goal. Okay? Yeah. So this is our most important goal. We may not be able to achieve it. Yeah. So we do not require data ordered. Yeah. Dynamic, this property is important. So we need to make our new data structure support dynamic data for deletion, insertion efficiently. Yeah. All right. So efficient sorting, because we do not consider order in this data structure, so it's not easy to provide ordered data. Yeah. So sorting also very expensive. Yeah. All right. So that's the new search algorithm in our mind. So we need to design a new data structure and a new search algorithm. Yeah. All right. So next, we need to start from this index search. First, we want to find its biggest problem. Then we find a solution. We want to fix that problem. Then we get a new solution, new search algorithm. Yeah. All right. Yeah. All right. Yeah. So let's look at the index search first. Yeah. A simple example, we can see what is its biggest drawback. Yeah. All right. In our textbook, or some other textbooks, other books called direct addressing, yeah, because you get array indexes, you find your data directly, right? So you'll find the address of your data directly. Yeah. So this method, yeah. So that's the reason. Another reason you do not see this word index search. So in our textbook, it calls direct addressing method. Yeah. Yeah. All right. The key property, there is one-to-one correspondence between the search key and the index of array. Yeah. The same thing. Yeah. The search key is the array index. Array index is the search key. Same thing. Yeah. So that it's key property. Yeah. Now the main problem. Yeah. This way, there is a huge problem. Yeah. So nobody wants to use it in the real world applications. Yeah. When the keys are long, yeah, the problem occurs when the keys are long. In this situation, and you only have a small number of elements in the array. In your data, relatively small number of data items, but the keys are long and long. Okay, in that situation, you have the big problem. The problem is this method wastes a lot of memory space. It wastes a lot of memory space. So that's the main problem. Okay, waste a lot of space. Okay, so here, let me use a concrete example to explain the problem and the improvement. How to use space efficiently. Long keys. Think about when we, because for the popular users' IDs, sometimes SSN or student numbers. So in companies, so they may have employee IDs, right? Because Social Security number, very sensitive, right? Here, in our discussion, so we use that as an example, but usually Social Security number very sensitive. So most companies, they provide their employees employee ID, okay? Employee ID, So so for students, so they use student ID, so they do not use Social Security numbers, But those numbers usually many digits, right? Student numbers, employee numbers, usually there are many digits, All right, something like this, But think about, if in a class, we only have 40 students. Here I just use relatively small number, okay? Compare your key size, the number of digits or number of characters, could be characters, okay, digits in the search keys, 40. So this 40 number is very small, okay? But if you want to use index search, you need to create an array. If you use this number as array indices. All right? Your array is huge. Think about array is huge. 9 digits. Think about array size, 9-digit number for your array size, but you only store 40 student data there. 40. So you waste too much space. 9-digit array, your main memory cannot hold it. Think about that. Your main memory, you do not have that much space in your main memory. So that's the reason this algorithm is useless. Okay? It's useless for this reason. Okay? It's useless. Okay? All right. Cannot use keys as indices directly. That means you cannot use direct addressing. You can only use indirect addressing. That means direct addressing, this method does not work. In order to make it work, you have to use indirect addressing, not direct. Okay? Change to indirect. Then it could work. There is a possibility it could work. All right. But how to make it indirect addressing? Then, another big design consideration. Big design consideration to make indirect addressing work. All right. How to make keys shorter? Your goal, you want to shorten the given keys. All right. So here the question is, these long keys these long keys usually come from some, IDs. Yeah. And those numbers, you have to use them. Okay. So these numbers, so you need to use these numbers. Okay. As IDs, right? Yeah. You cannot change them. Okay. You have to use these ID numbers. You cannot change them. Okay. Yeah. All right. But you cannot use them as search keys. Okay. Not as search keys. Your search keys. Oh, sorry. Search keys you can use not as addresses, right? Yeah, direct addressing. Yeah, not as addresses. Yeah, but search keys you can use original search keys. Yeah, but not as addresses. You cannot use them as addresses. Okay. Or so you have to change addresses, or you have to make your addresses. Yeah. So here, although we say make keys shorter, but actually we should say make addresses shorter. Yeah. Keys we can keep the original keys, but make addresses shorter. Okay. Because we have freedom to choose addresses of our elements, array elements. We have freedom. Okay, choose addresses of our array elements. Yeah, yeah. But we don't want to change the search keys. Okay, yeah. So actually, make addresses shorter, not keys. Okay, yeah. But addresses come from keys. Yeah. Addresses come from keys. Yeah. So here you can see we need to do a conversion step. Yeah. So here there must be a conversion step. Okay. This conversion step make the direct addressing method to indirect addressing method. Okay? Yeah. Before conversion, it's the direct addressing method. But after the conversion, then we get an indirect addressing method. Okay? Yeah. But the harder part is the detail, this part. How do you do the conversion? This is the main question. How do you do the conversion? What conversion is the best? So you want to solve this technical problem. What conversion is the best? Okay? Yeah. The best based on certain criteria, right? Yeah. The best. What do you mean the best? Best based on certain criteria. Yeah. All right, so we will talk about that. The criteria. Yeah. How to map keys to slots. Slots here means addresses. Okay? Yeah. We have some storage data structure. You need to create a new storage data structure, and there are a certain number of slots in the data structure. Yeah. So the addresses of those slots come from the search keys in with some mapping. So here you see this word, map word, from mapping. Yeah. The mapping operation. Mapping. Mathematical mapping. So specifically, you should understand this way. Map your search keys to the addresses of the slots in certain mathematical way, by certain math formula, by certain math formula. That idea, okay? That's the inspiration we got from that poor direct addressing method. Okay, yeah, all right. So now mapping strategy. Yeah. What is a good mapping? Yeah. So what properties do we need to get a good mapping? Yeah. So these properties. Fast calculation. Yeah. Because the mapping, when we talk about mapping, most of time we talk about some math formulas. How do you do the mapping? Yeah. We need to design some appropriate math formulas. Okay? So there, when you do the mapping, you plug in the search keys into those formulas, then you do calculation, and we want to have fast calculation. When you do calculation, we want a very fast calculation. Yeah. If your math functions are very complicated, integral, then derivative, then, a lot of complicated operations. Yeah. If it takes too much time, then it's not good. Okay? Yeah. So we don't want that kind of formulas. Okay? So we want our calculation where you plug in, so we can get the function value quickly. Yeah, that's the first property. Second property, evenly distributed among all the slots. Yeah. That's, think about because there is a possibility you may map several elements in the same slot, right? Yeah. Think about that situation. Yeah. It's a bad situation. Yeah. You map multiple elements in the same slot, so you get a collision problem. Okay? Then you need to resolve. You need to find some way to resolve the collision. Right? Yeah. So that problem. Then it takes time. It takes time to resolve the collision. Yeah. So then your search performance will be slow. Okay? Yeah. So if you can distribute the elements evenly among all the slots, then you can significantly reduce the collision problem. Okay? Yeah. So the second property also important. Yeah. You want to spread the data items as even as possible. It's hard. We know it's hard to spread evenly. It's hard. Yeah. But we want to try our best to get this property. Okay. All right. Third one, not sensitive to any pattern. Yeah, the pattern of data. So your data may follow some pattern. Yeah, think about the data could follow some pattern. Yeah, the search keys. Yeah. The search keys, have some special properties. Pattern here we mean some special properties. For example, your search keys are even numbers. That's a pattern, right? So your search keys are odd numbers. That's a pattern. Okay? So your search keys, has last digit 0. That's some pattern, right? So there are many different possible patterns. Yeah. But when you design your mapping functions should be very robust against those patterns. Okay? In other words, your math formulas, functions should be able to break most of those patterns. Break those patterns. Okay? If you can break those patterns, then your mapping function is very robust. Okay? Not sensitive to any pattern. Okay? Yeah. So think about these design requirements. Yeah. How to construct a data structure supporting efficient search algorithm. Yeah. All right. Implementation. Yeah. Choose appropriate math functions. Yeah. So we call them hash functions. if, so here, the method is very simple. Yeah. If you can find appropriate hash functions, then we almost done. Yeah. So the whole data structure search algorithm is almost there. Not much work. Here you can see the method is very simple. Yeah. But the result is very good. Yeah. All right, so that's the reason I want to introduce. Even in our last formal lecture class, I like to give you the background of this method. Yeah. It could be very useful in your real world situation. Yeah. All right. C.2, hash function. The first type of simple. Yeah. So we want simple functions. The first type, division method. Yeah. It may not be a good one, but as our first method. Yeah. First method. Let's start from the division method. The second one, I want to talk about multiplication method. Yeah. Yeah. Then for our background, it's enough. Yeah. Yeah. Because the multiplication method already, it can help us break most of the data patterns already. Yeah. So, all right. Hash function design, division method. Yeah. So for simplicity, we assume all keys are natural numbers. Yeah. Because in the real world situations, your keys could be string characters. Yeah. So characters in a string. Yeah. That you can also apply this method. So if you get a string key, you can convert to numerical numbers, right? You can find a way convert your string key as numerical numbers. So no problem. Yeah. So it's simple, straightforward. Yeah. Yeah, but here we just use natural numbers. Yeah. Can be converted. Yeah. Easily. Yeah. All right. So there are m slots. So our hash table, so we call our data structure hash table. Our hash table, here we can choose this m number of slots. Yeah. So you can make a decision to choose certain number of slots, m slots. Okay. All right. How to map a relatively large key k to one of the slots. Yeah. 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 Although we know there is a possibility two different keys could be mapped into the same slot. Yeah, that's possible. So that's the collision problem. So we will discuss, how to handle the collision problem later. Yeah. All right. So the first method, we use this mod operation, modular, integer division. Yeah. When we do integer division, yeah, k over m, we only take the remainder. So this mod operation tells us we just keep the remainder. Okay? We keep the remainders and we throw away the quotients. We throw away the quotients. Okay? We only keep the remainders. Yeah. All right. Yeah. First, it's easy to calculate. Very fast. Easy. Okay? All right. Yeah. Evenly distributed may not be evenly distributed. Yeah. So this one, yeah. So simple, it may not be robust. Okay? Although it is simple, but this method, usually it is not robust, not very robust. Okay. Later I will show you some example. Yeah. Some special patterns that can break this method easily. Yeah. All right. So it depends on keys. If your keys have certain pattern, then you can make this method make its performance very poor. Okay? Yeah. Very poor. Yeah. Yeah. Called by any pattern, yeah, some pattern. Yeah. So let me give you a simple example. Yeah, let me see how much time I have. Yeah, good. I still have at least 10 minutes. Yeah. Yeah. All right. In the division method with m slots, look at example 1. Suppose m equals 15. Okay? Yeah, this number, 15. Yeah. And our hash function is h of k equals k mod 15. Yeah. Now our data, if our data has this pattern, our key values are multiple of 3, are multiples of 3. That's the pattern. All the key values are multiples of 3. Okay? If we have this pattern of data, then its performance is very poor. Because we know 15 is a multiple of 3, right? 3 times 5. 15 is a multiple of 3. Yeah. So then you do the division by 15, you keep the remainder, and that remainder is also multiple of 3, right? Yeah. Because let's look at this. Yeah. Because the difference of the hashed key number, hash function value, and original key value, the difference must be a multiple of 15. The quotient, remember the quotient. We throw away the quotient. Yeah. And the 15 is the divisor. Yeah. So it should be 15 times some quotient, right? Yeah. So then your h of k equals 15 and minus k, but the k is multiple of 3. Okay? So you can get a common factor 3 from these two terms. Common factor, you can factor 3 out. So h of k must be multiple of 3. All right? Yeah? If it's multiple of 3, then your mapping addresses for those slots have to be multiple of 3. Then you can only use 1/3 of the slot locations, right? Yeah. For example, location 0 you can use, location 3 you can use, 6 you can use, 9, 12, and so on, right? Yeah, 15, so 14. Yeah, suppose the largest slot number is 14. Yeah, only the slots with these numbers can be used, and the 2/3, the slot number other than these 5, 2/3, 10 of the 15, you can never map your data to those slots, right? So you waste 2/3 of the storage space. That means your performance very slow, very poor. Your overall performance, okay, search performance, very slow, poor. All right, yeah. So it's not robust for this special pattern. Yeah. So you need to fix this problem. Okay. All right. So how to make it robust? Another example: division method with m slots, but this time if your m equals the power of 2 number, then there is some pattern that can easily break this method. Yeah. So suppose our hash function equals k mod 2 to the r. The pattern, if 2 keys have the same last r bits, think about that. Yeah. So you have some keys with the same last r bits, then those keys will be mapped to the same slot. Right? Yeah. Yeah. After the modular operation, they are mapped to the same slot location. Then you need to handle the collision problem. You need to spend a lot of time to handle the collision problem. So your overall performance overall search performance will be very slow. Yeah. So this is another example, where you have a very bad hash function, so your search performance will be very slow. Yeah. All right. A good choice. So, as a summary, yeah. So when we design a good hash function, so we want to, try to choose some good hash function. Yeah. Yeah. So a prime number that is not too close to any power of, yeah. When we choose n, remember the first time 15, it's not a prime number, right? Yeah. So it has a non-trivial factor 3 and 5. So if we choose a prime number, then we won't have non-trivial factor, right? Yeah. So here you can see the prime number is good. Okay? The prime number is good. But if the prime number is very close to power of 2, so then, when we modular, so there is a problem, if the last R bits, very close, so there is a possibility those numbers map it to the slot numbers in a small range, the small range. So we don't want make that prime number very close to power of 2. Yeah. Yeah. Because we don't want to map some keys to a small range. Yeah. Yeah. All right. So it is expected to be robust against any pattern. Yeah. But that's very hard. Yeah. So we want to break all the patterns. Yeah. It's impossible to break all the patterns, but we want to break most of the patterns. Yeah. Yeah. All right. Yeah, it's empirical. Yeah. So here, because we cannot prove it. Yeah. The hard part is it's very hard to prove, some hash function can break how many patterns, so basically empirical. Okay. You just do experiments. Yeah. And see how well it performs. Yeah. It cannot be proved. Yeah. So this part, cannot be proved. Yeah. So we rely on experiments to tell us, it's good or not. Yeah. All right. It is possible to create a special pattern to make it perform. Yeah, because so here, no matter how you design a hash function, there is some way. Yeah. So, although sometimes it's very hard, but it's possible. There is a special pattern. If you create a data with some special pattern that can make this particular hash function perform very poor. Yeah. 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 But the probability is small. Yeah. If the probability is small, we don't worry. Okay. Yeah. So there is a bottleneck. Okay. So we know it's very common. So many algorithms have some bottleneck. Yeah. So for example, quicksort has bottleneck, right? Yeah. Quicksort, although it's very useful, but it has some bottleneck. Yeah. Yeah. So here for our hash function, it's possible there is some bottleneck. Yeah. All right. Yeah. Let me see how much time, if I have a few more minutes. Only 4 minutes. Yeah. Yeah. All right. 4 minutes. I cannot go very far. So let me just so the remaining part. Yeah. I try to find some time record videos for your interest. Yeah. So you do not need to spend. You don't need to if you want to focus on your final. You don't need to spend time learning this part. Yeah. But after your final, so if you are interested in this topic, complete the story, then you can just watch the video. Yeah. And I won't give you question after this line, okay? Yeah, after the C.3 line. Yeah. Before this line, I may just give you simple questions, okay? Straightforward, simple questions. Yeah. Some basic facts, okay? Yeah. So it should not be very hard. Yeah. Very simple. Yeah. All right. So that's for all our formal lectures. Yeah. So then the next week, our last week of the semester, we will do review first, then you need to come to school for the final, okay? Wednesday, yeah. So if you have any question related to the time, schedule, convenience, you let me know. Yeah. So I will try my best to arrange, convenient way for your final, okay? Yeah. So otherwise, just come to, yeah. So I will post announcements to give you more information about the final. So, all right, so now we finish everything right here for this semester, and I will start making hint videos tonight, and I will post one by one. So after